Okay, so in this section, we're going to look at spatial statistics. This isn't a full spatial statistics course. The goal here is really just to introduce you to some of the methods we use to describe our data and look at relationships within our data. So if you're interested in taking a more involved course in spatial statistics, I would recommend our Geographic Data Analysis course, which is Geography 300. All right, so what makes geographic data unique? So here are some reasons. So first, it occurs over a map surface. So that indicates that the data may be spatially correlated, that the samples may not be independent of each other. So it's not just independent records from a table, but features that occur over a map space and are at variable distances from each other. Second, you may have a spatial autocorrelation in your data. So we'll talk about this later, about how it's assessed and quantified. But a lot of statistical tests assume that your data points are independent of each other. And if there's spatial correlation, that means that there is inherently some correlation between your samples, or that they're not independent. Other than just having correlation across space, you can also have correlation across time, so temporal correlation. So for example, if you were looking at climate data collected at a weather station, you would expect samples that were collected closer to each other in time would be more similar than samples that are further away. So for example, if you were interested in looking at temperature data, you would expect that temperature measurements recorded close together are going to be more similar than random temperature measurements recorded further apart. As we talked about in the last section with the modifiable areal unit problem and the ecological fallacy, your analysis might be impacted by the geographic unit of measurement. So you would expect to get different answers if you say aggregated data on the census tract versus the census block or block group or county. So that spatial aggregation and scale is a component of the analysis. Also, your results may vary with time. So for example, if you look at relationships, say like demographic or voting or political data back in, say, the 1970s, you wouldn't expect to see the same pattern at all the same locations in the current time period. So obviously all of these points are not necessarily specific to just geographic data, but this is supposed to show that there are some concerns and issues when we worry about dealing with geographic data specifically, and we should take those into account when we do our analyses and interpret the results. Okay, so we're going to begin with exploring your data. So how can we visualize our data graphically and look at like the distribution, such as central tendency and variability of our data. So a lot of this early stuff won't necessarily be spatial, meaning that a lot of these techniques or measures apply to any type of numeric data, not just to data occurring over map space. All right, so first we're going to look at ways that we can look at just a single variable using univariate graphs and then some types of statistics. So univariate basically means one variable. So you're, again, just looking at one variable at a time as opposed to trying to, say, look at the relationship between two variables or multiple variables. And there's a couple of different ways that we can do that graphically. One of the first options we're going to look at is simply a histogram. So in a histogram, the y-axis is generally going to be frequency or count, so this represents the number of features occurring, and the x-axis represents the actual data values. So for example, in this image, or in this example, we have depths and represented on the x-axis, and then on the y-axis we have frequencies. So the higher the bar, the more measurements occur within that range. Note that we have to bin the data, so instead of just looking at finite data points, we look across a data range, and these are each of the histogram bins. Generally, if you make the bin smaller, you're going to see more local noise in the data, more local patterns, where if you make the bins bigger, that means that you're going to see kind of a more generalized pattern. And there's really not a right answer in terms of how wide each bin or how many bins you should, how wide each bin should be or how many bins you should have. So anyway, in this data set, this gives us a sense of the distribution of the data. So we can see the majority of these depths are around, say, -5, and there's a long tail out here into the deeper or more negative direction. So we could say that this data is a bit like a left tail heavier skewed to the left. So anyway, that's an example of a simple graph where we can just look at data distribution. So the range of values, essential tendency of the values, and whatnot. Another method we use to do this is a kernel density plot. So this is actually the same thing as a kernel density surface that we use in GIS, except instead of looking in two-dimensional space, we're just looking at this one-dimensional graph space. So the height of the graph represents the density or the frequency or how often measurements occur. And here we're looking at 3 different groups. So this is specifically for miles per gallon for different types of cars. So as we can see here, 4-cylinder cars tend to have higher miles per gallon. 6 cylinders are in the middle, and the 8 cylinders are at the end. It looks like there's also more dispersion in the 4-cylinder data than there is in, say, the 6-cylinder data, and maybe the 8-cylinder data is a bit multimodal, so there's more than one kind of hump here. So instead of just binning the data and counting the number of features in bins, we're fitting a smooth kernel density function through the data to assess the distribution of values. Since the x-axis and the y-axis can basically be the same for a histogram and a density plot, sometimes you'll see these two plots plotted or created together in the same space. Okay, so those are some simple graphs for just looking at the distribution of a single continuous or numeric variable. We can also look at this statistically, and a lot of these I'm sure you probably have heard of or seen before. So, for example, we have the mean. So the mean is just simply summing all the values and dividing by the number of samples. And that is generally expressed differently if you're talking about the mean for an entire population or a sample from a population. So mean versus x bar, which is an estimate of the mean of a population from the sample. The large N here denotes the entire population, the number of samples in the entire population, where N denotes the number of samples and the sample from the population. Okay, so we're effectively just taking the average. So summing them up, dividing by the number of samples. There are other measures of essential tendency, though. Another example or option is the median. So the median is the most middle number. So, or the 50th quartile, 50% quartile, 50% quantile. So effectively half of the values fall below this number and half are above the number. So it's the most middle. Another option is the mode, which is the most common number, so the most commonly occurring value. Sometimes there's a mode, sometimes there isn't if all the values are, say, unique. One thing to note about measures of essential tendency is that means tend to be more impacted by outlying data, high or low values than the median or mode is. So sometimes when we're worried about that, we will use the median to assess essential tendency as opposed to using the mean. Okay, so that's just part of the story. You also, other than just looking at the central tendency of the data, it's also important to look at the variability or dispersion of the data. And generally we do that with some different measures of variability. Maybe the simplest is just the range. So that's just the maximum value minus the minimum. So the range of values within the data set. So if, say, test scores range from 95 to 60, then you would just subtract those two to get the range of test score values. One thing about range is similar to mean, it can be heavily impacted by outliers. So for example, if most people in, say, an exam got 60 or higher, but one student got, say, a 20, then that outlier would greatly impact the range of values. The most common techniques used to look at variability is generally the variance and the standard deviation. And here you can see two different formulas. Again, one is for a population and one is for a sample from that population. You can see different symbols here for population variance versus sample variance. Here we're dividing by n minus 1, which relates to degrees of freedom, and here we're dividing by n. Okay, so variance is actually fairly simple. You just take the value and subtract the mean value from it and square it. Then you sum those up and divide by n. Note that since you're squaring the difference, the result is going to be in the square of the units of the variable. So if you're assessing, say, depth in meters like we were looking at earlier, then what the units you would get out here would be meters squared. That's one issue with variance because you've changed the units. So what we tend to do with that is we take the square root of it so we get the units back. Now this is a trick you see a lot in statistics where we we take the square of data and then take the square root. So we can deal in that sense. It allows us to deal with absolute values as opposed to dealing with signed data, and then taking the square root, we get the original units back. So effectively, again, this is just the difference between all the samples and the mean added up, or squared, then added up, and then divided by the number of samples. The standard deviation is, again, just simply the square root of the variance. So you just take the square of it, and again, you get the units back. So by using something like the mean and the standard deviation, we're able to describe both the central tendency of the data and also the variability or dispersion of the data. We can also compare by groups. So we can look at the means and the standard deviations for different groups to see how they compare in terms of, again, central tendency and variability. Okay, another tool that we use to look at data distribution is a box plot. I really like box plots because I think they actually tell you a lot about your data, and they're pretty easy to interpret, and you can also use them to compare the distribution between groups, which we'll look at in a minute. So on a box plot, we have the following things provided. So we have the minimum value, the maximum value, then we have the first quartile, the third quartile, and the median. So just so you understand what these values mean, the minimum is the lowest number, so no values occur beneath it. The maximum is the highest number, so no values occur above it. So 0% of the data are lower than the mean, 100% of the data are lower than the maximum. 0% of the data is smaller than the minimum, 100% of the data is smaller than the maximum, so they fall within that. So effectively, this is the range, right? But that's not labeled here. The first quartile is a division where 25% of the data fall beneath that value and 75% fall above it. In contrast to that, the third quartile is basically the opposite. So 75% of the data values are smaller than it and 25% are larger than it. The median is effectively the second quartile. So that's where 50% of the data is above and 50% of the data is above. So half and half. So again, this is basically allowing us to look at our central tendency using the median and also the variability in the data by looking at the range of values and also the IQR. The IQR, interquartile range, which is labeled here, is simply the difference from the first quartile to the third quartile. So this is the IQR. So in both the IQR and the min-max difference or range can be used to assess variability. One thing to note is that the IQR is generally less impacted by outliers than the range or min, max, minus, min. So we tend to use that if our data have outliers. Note that sometimes data points that are considered outliers are actually plotted as points on this graph. That's not pictured here. And there's different definitions of how you would define an outlier. One common definition is to use any high points or label any high points that are greater than 1.5 IQR from the third quartile as outliers, and any low points that are greater than 1.5 IQR from the first quartile as low outliers. But that's not a hard rule. And as you see here on the slide, that provides some information in regards to what those different measurements mean. So hopefully this is helpful. Again, one of the uses of this is to be able to look at the distribution of your data and also to compare groups. So here's two examples where we're comparing groups. So here we're looking at runoff in millimeters, and we're comparing them across months. So again, using this data, we can look at both central tendency. So we can see that there's generally more runoff through the winter, and then drying up through the summer, and then picking up a bit again through the late fall. And other than just looking at that seasonal trend in central tendency, we can also look at variability. So generally it looks like there's less variability in the summer months in runoff than there is in the spring months. So, but again, both variability and central tendency. The points here represent high outliers that are more than 1.5 IQR from the third quartile. Here's another example using the car cylinder data. So here we can see the distribution of miles per gallon, similar to our previous density graph, but now as a box plot. So again, central tendency-wise, 4 cylinders tend to have better gas mileage compared to 6-cylinder compared to 8. And in this case, it also looks like there's more variability in the 4-cylinder data than the other two. So again, allowing us to explore our data. Here's another example that's a remote sensing geographic example. So here we're comparing the normalized difference vegetation index, or NDVI, for 4 different land cover types. So it looks like in this case, woodlands had the highest NDVI, and then it looks like forest and herbaceous areas were actually fairly similar, and barren areas and water were lowest, which makes sense for NDVI. Other than just looking at central tendency, we can also look at variability using the range of values and the IQR. So for example, it seems like there's more variability for, say, herbaceous cover and water than there is for, say, barren. Again, note that there are some labeled outliers here that are less than 1.5, low values, that's greater than 1.5 IQR from the first quartile, or again higher than 1.5 IQR from the third quartile. So again, allowing us to compare our data. Okay, so now we're going to move on and look at graphs where instead of just looking at a single variable or a single variable by group, we're going to look at least 2 variables. And here we're going to talk mainly about scatter plots. So in a scatter plot, you're using the x-axis to represent one variable and the y-axis to represent another variable. So you can see if there's a relationship. So for example, in this case, we can see that for car weight increasing in this direction and miles per gallon increasing in this direction, there seems to be an indirect or inverse relationship. So as a car gets heavier, its miles per gallon tends to decrease, as you would expect. So it does seem that there's a trend in that data. Note that you can include other graphical parameters in a model or in a graph to try to see additional relationships. So here we're showing the number of cylinders using a collar and the horsepower using the size of the cylinder. So we can see very clear clustering here of the number of cylinders for 4s, 6s, and 8, and how they relates to miles per gallon and car weight. So again, assessing the relationship between multiple variables. Here's another example. So this is gross domestic product per capita, so per person. So here what we're seeing here is the comparison between gross domestic product and life expectancy in years. And there's a very interesting trend there. Again, using color and size to show population of this country and the continent the country occurs on. Another extension of the scatter plot is what's called a scatter plot matrix. So a scatter plot matrix allows you to not just compare 2 variables, but you can compare 2 variables pairwise for the entire data set. So for example, here we're comparing percent canopy cover to NDVI and brightness and greenness and wetness, which can be calculated from the Landsat scenes. So again, we can look at the distribution of the data and see if there's relationships between the variables one by one. This axis represents the distribution of the variables as a histogram, and all the things off the diagonal axis are the relationships. So here, for example, we're comparing principal component and NDVI, and we see a bit of looks like a positive correlation there, but it's pretty noisy. Here we're comparing wetness and principal component analysis. This relationship appears to be more negative. So brightness and wetness, for example, seem to be more negatively correlated. All right, so one component of talking about data distribution is that sometimes we want to compare our data to a theoretical or kind of like standard distribution. And one common distribution that we use is what's known as the normal distribution. So here's the characteristics of a normal distribution. So first off, it's bell-shaped, so it takes on this bell-shaped curve. The mean, the median, and the mode are equivalent. So in this case, this red line here represents the mean, the median, and the mode. So all the measures of central tendency are the same value. This curve is symmetrical about the mean. So for example, if we folded this graph along this line, each side, they would line up perfectly, so it's symmetrical. The actual shape of the normal curve varies based on the mean and standard deviation of the data, but no matter what, it has to have these criteria. So 68.3% of the data are within one standard deviation of the mean. That's this darker blue area here. So 68.3% of the data will fall in that data range. So that's one standard deviation. 95.4% will occur within two standard deviations of the mean. So that's this entire area here. And then lastly, 99.7% of the data lie within three standard deviations of the mean. So that's extending out to this lighter blue area here. So that leaves only 0.3% of the data, which is outside of the three standard deviation range, and both in the positive direction away from the mean or the negative direction away from the mean. So why do we worry about the normal distribution? Well, a lot of statistical tests actually have this as an assumption in terms of, say, the distribution of like the y variable, like for example with regression. So certain statistical tests will not be valid unless your data approximates this distribution. Unfortunately, as you probably imagine, a lot of real data don't have this distribution characteristic, and thus it might not be appropriate to do certain types of tests with that data. Okay, so how can data be different from normal? So there's two kind of measures of that. One measure is skewness, and that's basically a measure of symmetry. So your data can be skewed to the right or skewed to the left, or have a tail to the right, a tail to the left. So in this image, this orange line would represent data that's skewed to the left. So it has outlying low values, so it has a tail to the left. In contrast, the one that's blue indicates skewed to the right. So data, there are some outliers or high values as opposed to low values. So that's skewness. There's actually a statistical measure for that called skewness, and here's roughly how you interpret it. So if it's negative, that would suggest skew to the left. So this orange line would yield a negative skewness value. If it's positive, that indicates that it is skewed to the right. So again, this blue trend. And if it's near zero, that would indicate that it's roughly or close to normal, or there's no skewness issues. In contrast to that, kurtosis is used to look at how heavy-tailed or light-tailed a distribution is based on comparison to a normal distribution. So is it much wider, more spread out, or more variable, or heavy-tailed than a normal distribution, or is it light-tailed? Everything tends to be kind of centered. In this example, this yellow curve represents what we call a leptokurtic distribution, and that's less variable or more kind of pointy or light-tailed than a normal distribution. Note that the central tendency is roughly the same, it's just the distribution or variability is different. This black curve represents a normal distribution, and then this red curve represents what we call a plesiokurtic distribution, so it's more variable or more heavy-tailed than a normal distribution. And again, there are statistical measures for kurtosis as well as skewness. One tool we use to look at the distribution of our data in comparison to a normal distribution is the normal QQ plot. And we have one pictured here. So the idea is that you compare the quantiles of your data to the theoretical quantiles, and these theoretical quantiles would be the quantiles of the data if they actually were normally distributed. So if your data are normally distributed, the points should fall roughly along this line. If the data are not normally distributed, then they're going to diverge from the line in some way. Here's some general trends. So if the data falls along this line, so that would indicate that the actual data quantiles are fairly similar to what they would be if they were actually normal, or the theoretical quantiles and the data quantiles are somewhat comparable, then again it falls along the line. If it's concave, then that would indicate that it's skewed to the right. If it's convex, skewed to the left, and if you have divergent at high or low values, then that would indicate some issues with kurtosis. Here's some examples. So here we have a normal distribution. So as you can see, the points fall roughly along the line. So that would again indicate that it's roughly normal because the theoretical quantiles and the actual quantiles are similar. Here we have skewed to the left distribution, so some outliers to the left. And as you can see here, we get a convex shape, so diverging in a negative direction from the line at high and low values. You get the opposite pattern if you have a skewed to the right type distribution. So again, more of a concave shape in the QQ plot. Here we have a leptokurtic distribution, so it's more pointy or light-tailed in comparison to a normal distribution, and you can see the divergence at high or low values. And then we kind of see the opposite pattern when we have a plateokurtic distribution, which is heavier tailed in comparison to a normal distribution. So anyway, this is a very useful graph for assessing the normality of your data. So looking at these graphs, looking at distributions using density plots or histograms, and also making use of skewness and kurtosis measures can help you kind of understand your data a little bit better. Before we move on, I wanted to mention a free software package called GeoDIS. So here's a link to the website. Here's a screen capture from the software. So again, if you go to this site here, geodiscenter.asu.edu, you can download the software for free. And this provides some additional functionality in terms of data exploration, and spatial statistics, modeling, regression, that can accompany like things like ArcGIS or QGIS or whatever. So if you're really interested in this stuff, I would recommend downloading it and playing with it. It's actually pretty intuitive and easy to use. Okay, so our next topic is going to be sampling. So it's generally not possible to measure every member of a population. So for example, if your study pertained to all the people on the earth, you're not going to be able to measure every person on the earth. If it was every student at this university, that would even be difficult. Obviously, with small populations like within a specific family or people that live on a certain street, it might be possible to actually measure everybody or collect data for everybody, but generally that's not possible. So we tend to have to sample from the population and then draw conclusions about the population from the sample. So here's some points on sampling. So a sample is a set of measurements taken from a larger group or population. So it's a subset of students at the university that are going to be used to represent the entire student population. The sample means and variances can serve as estimators for their populations. Again, earlier on we saw different formulas for population, standard deviation, and variance, and mean, and then sample standard deviate or mean, sample mean and population mean. So this is why we're estimating something about the population from the samples. Generally, it's easier to measure with samples, then draw conclusions about the entire population, because it's generally impossible or difficult or expensive or whatever to measure everybody. But the main thing you need to know about this is that if you want to try to draw some conclusions about the population from a sample, then you need to have a unbiased representative sample of the population. If there's any bias in the sample, then you can't assume that it actually represents the population correctly or adequately. So how do we do that? Well, generally we do that by undertaking or making use of random sampling. All right, so I'm going to talk about some of the different sampling strategies that are used to collect samples from a population in the context of geographic data. So the simplest is just simple random sampling. So the idea is that, say, you'd have a spatial extent, and within that extent you just randomly create X, Y coordinate pairs that become your samples. So you use some type of random number generator that would generate, say, easting and northing or latitude and longitude pairs, and that becomes your sample. So as you can see here, there's really not much of a pattern in these points. They're just randomly spread out across this study area extent. Note that you can augment this. So for example, you can do random sampling, but have a defined minimum distance between points. So for example, some of these points occur fairly close. If you wanted to have a minimum gap between them, then you could specify that. Another option is systematic sampling. So the idea here is that we collect data on a regular repeating pattern at a fixed distance. So as you can see, these are all spread apart evenly. So say we're collecting a data point every 10 meters or every 30 meters. So that's systematic sampling. Note that both of these methods you could apply not just in the spatial domain, but also in the temporal domain. So we could select random points through time or systematic points through time, like every half hour, for example. But again, we're focused here mainly on spatial. And then here's an example of systematic sampling along transects. You'll see this used a lot in like forestry applications or ecology field sampling. So the idea here is that you create a transect, and then you systematically sample points along that transect, like on a regular repeat basis. Generally, the transects are supposed to be randomly sited in some way. You can also have random sampling along transects, where instead of having an even space, you're just randomly collecting data along this line or these different lines. Okay, a technique I use a lot is stratified random sampling. So this could be used if you want to get an equal number of features per like a map category. So for example, here we're showing examples by land cover type. You could also have it by vegetation type or soil type or land ownership or zoning or something. So again, you're basically stratifying the random sample so you get a certain proportion or maybe even an equal proportion of data in each type. So here we're getting an equal number of map features in each of the mapped land cover types. So it's random sampling, but it's stratified based on a categorical or nominal variable. And then lastly, we have random sampling within clusters. So the idea here is that you create clusters, and then within those clusters, you create random samples. Why would you do this? Well, if this was a very large extent, it might be nearly impossible to actually create random samples throughout the entire extent and be able to actually get to them or survey them or whatever. So if we create small subset areas, then that would allow us to actually have a smaller unit that we could go to and then do random sampling within. Again, this could be a bit problematic, especially if the clustering units are not randomized in some way, so you might induce some bias. Again, you could take a whole series of complex advanced courses on how you design studies and do sampling. But the key thing is that in order for you to really be able to extract useful information from your data, extract from your sample back to your population, or infer from your sample to your population, then it's very important that you that you have an unbiased sample from your population. Okay, so I just wanted to mention some tools that you could use in, say, the ArcGIS environment and other environments to do this type of sampling. QGIS and R both have some very powerful sampling tools. For example, in R, I really like the dplyr package. It's got a lot of very useful sampling methods. Within ArcGIS Pro specifically, there are tools to generate random points within a bounding area or extent. You can also generate points along a line vector object. You can produce tessellations and fishnets. We'll talk about those in a minute. Here's some example tools for generating that allow you to create random points within a geographic extent. So here you can define an extent, and you can define the number of points that you want. You can also specify a minimum distance between those points so you don't have a lot of samples that are, say, really close together and maybe correlated. And here's the tool for generating points along a line. So you can input a feature, output point layer, use a distance, and then specify the distance that you want between the points. Here's an example of a tessellation. A tessellation basically takes a geographic extent and breaks it into homogeneous areas of the same shape and size. Generally, this has to be done with features that can be combined in such a way that it can fill an extent without any overlap. So here's some examples in West Virginia. Here we have hexagons. That's a very common tessellation technique. Here we have triangles, and here we have squares of variable sizes. Again, why would you do something like this? Well, if you had to aggregate the data and you didn't have a good aggregating unit to use, like, say, counties or census tracts or watersheds or whatever, you could create this systematic sampling or tessellation and then summarize on that. So, for example, count the number of pollution discharge points in each of these, and then assess whether there's any spatial pattern in that in the discharge points. One thing nice about this is, since you have units that are roughly the same, then this can help alleviate the scale effect issue associated with the modifiable aerial unit problem. When you do create a tessellation, it's important to think about the size of the tessellation and which shape you're going to use. Again, I really like hexagons for this. Another concern is when you have a very odd-shaped feature, like West Virginia, you're obviously going to have some partial features along the edges. So you might have to think about how that may impact your analysis. Another process, and this is less applicable here, but I thought I'd mention it, is the creation of a fishnet. So this creates basically a rectangular grid across a geographic extent. So you can use this for some type of systematic sampling. So sample X number of points in each of these cells, for example, sample where they intersect. I have used this a lot more in the context as a guide when I'm drawing or digitizing as opposed to in a sampling routine, but I thought I'd mention it here. Okay, so now we're going to move on to the second section here of this spatial stats lecture. So now we're going to focus on not looking just at the data values and looking at their distribution and central tendency, but instead we're going to look at the spatial measures of central tendency and dispersion. This is obviously something that's fairly unique to geographic data and doesn't necessarily have a surrogate in other types of data, like a bunch of values in a table. Okay, so one of the simplest techniques that we can use for assessing the spatial central tendency of our data is central feature. So effectively what this does is of a set of points, it finds the point that is the most center within the data set. So again, it identifies the most central feature. In this case, the central feature is defined as the feature in the data set with the smallest accumulated distance from all other features. So it's basically, if you'd sum up the distance from one feature to all of its neighbors and then do that for every single feature, the central feature is going to be one that has that smallest accumulated distance. So it's on average like the closest to all of the features. Note that your output is going to be one of the features. So for example, here we have airports that are above a certain size, and this airport here was selected as the center airport in the data set, which means that it has the smallest accumulated distance from all the other airports mapped in this data set. When you create these types of outputs, you can use different measures of distance. One option is Euclidean distance, and that's simply the straight line as the crow flies distance between locations. And that's commonly what we use. This is the same distance that we use when we are creating, for example, a Euclidean distance grid. An alternative to that is the Manhattan distance. The Manhattan distance is the sum in the x and y directions, easting, northing, latitude, longitude. So again, this is like a city block thing. So you have to go over and then up. You can't just go straight across. So that's another way that you can measure distance. Generally, Manhattan distance is going to be a larger number than Euclidean distance. Because, obviously summing up the x and y direction is going to be longer than just the straight line distance. It's also possible to apply weights. So, for example, with these airports, if we had like a measure of the number of people that use that airport in a given amount of time, we could use that as a weight. So airports that had higher traffic would have a higher weight in this calculation of accumulated distance than airports that had less. You can also stratify by category. So, for example, let's say we wanted to have let's say we had colleges, and we had the different types of colleges, like four-year liberal arts colleges and large research universities and junior colleges and tech colleges and whatnot. We could actually get separate central features for each of those groups. And you could also apply weights and categories. Okay, another way to investigate central tendency is to calculate the mean and or median center of your data. So here's a definition for the mean center. So it's the average x and y coordinates from the features, whereas the median is the median x and y coordinates from the features. Note here that generally now you're not selecting one of the features, it's just going to be a geographic coordinate that meets that criteria. So it's not necessarily going to line up with one of the input features or airports in this case. So you can see, as you can see here, the mean and median center is shown here in green and yellow, and I forget, actually it says here. So green is mean center and yellow is median center. They don't actually land on one of the airports. So again, a new location is generally selected as opposed to one of the input features. Similar to central feature tool, you can apply weights, and you can also get mean or median centers by category. So not just for the entire data set. So different ways to do it. This is, again, not going to be one of the features in the data set, whereas the mean center, whereas the central feature would be one of the features. Okay, so as we talked about earlier when we were trying to summarize like numeric or continuous data, the central tendency is really just one component of the story. We also need to worry about the variability. In this case, we're going to be looking at variability in terms of space, so how spread out the features are. And there are two different measures for that. One option is the standard distance. So here is a definition for that. So it measures the degree to which features are concentrated or dispersed around the geographic mean center. So as you can see here, this green dot represents the mean center, as we talked about earlier, and then you plot a circle around it, which is a measure of how spatially dispersed the data are. The smaller the circle, the less dispersed they are. The larger the circle, the more dispersed they are, as mentioned here. You can specify the number of standard deviations if you want. So this is showing one standard deviation, but you could plot 2, 3.5 standard deviation, whatever. You can also apply weights, similar to how we talked about before, and you can stratify by category. So you get different standard distances for different, say, types of airports or different types of colleges or whatever. Okay, so that adds the spatial variability, spatial dispersion component, but you're not really looking here at any directionality. So what if the data were more spread out in one direction, say, than another? So that leads to the next tool, which is the directional distribution or standard deviation ellipse tool. So this creates an ellipse that summarizes spatial central tendency. Again, the mean center will be in the center of the ellipse there. Spatial dispersion, so how large it is, and then the directional trend. So here we can see that the data are more spread out in this direction as opposed to this direction, which kind of makes sense based on the shape of the country. So what we're really adding here is that trend. So we're not, the first two we kind of had before with the central feature, or sorry, not central feature, mean center, and spatial, and the standard deviation ellipse. But now we're adding the directional trend, so we have this more ellipsoid shape, right? So elongate in this direction, more spread out in that direction. Similar to the other tools, you can also apply a weight and also obtain this result for different categories. Okay, so now we're going to look at actual spatial statistics. So answering some type of spatial question using a statistical measure. Okay, so before we do that, we need to do kind of a general discussion of how you interpret statistical tests. Again, if you had a full-blown statistics course, you would talk about lots of different tests and how to interpret them and talk about different types of distributions and different types of scores. Here, I just want to briefly describe how we determine whether the result of our test and what it means. Okay, so generally with the test, there's going to be a null hypothesis. So that is the test where there is no statistical significance or difference. So basically, if the null hypothesis is not rejected, that indicates that there is no difference, or your tests show no difference for whatever it was that you were trying to determine the difference about. If the alternative hypothesis is that there is a statistical difference, or statistical significance or difference. So whatever you're testing does seem to be different between, say, the groups or based on a reference. So you can either reject the null or fail to reject the null hypothesis. This is the symbol for the null, H sub 0. This is the symbol for the alternative, H sub A. So if the statistical test does not show statistical significance, we fail to reject the null hypothesis. So HO. If a specific statistical test will commonly produce some type of statistic or index, and you'll see some different statistics and index used here. This is then compared to a distribution such as a z or normal distribution, and we use that to obtain a z-score, and then from that we can obtain a p-value. And the p-value is generally what you're going to actually be assessing. So for example, we commonly use a p-value of 0.05 as our cutoff. So if our p-value is less than 0.05, then we reject the null hypothesis, and if it's greater than 0.05, then we fail to reject the null hypothesis. So what does a 0.05 p-value actually mean? Well, all of these statistical tests are generally based on probability. So what's the likelihood of something would happen just by random chance? So for 0.05, that basically means that there's less than a 5% chance of obtaining the result by random chance. So this is equivalent to a 95% confidence interval. So again, if you set your p-value to 0.05, that would indicate that there is there's basically less than, if your p-value is less than 0.05, then that means there's less than a 5% chance that you would have got that difference simply by random noise or random chance. That's the idea. So generally with these tests, you're going to end up with an index, and then from that we can get a p-value, and then if it's less than our threshold, then we can say that there is difference. If it's greater than our threshold, then we fail to reject the null hypothesis. Okay, so we're going to start off with arguably the most simplest spatial statistics, and those are statistics that are designed to just simply look at point patterns. So whether a point pattern is random, dispersed, or clustered in some way. Okay, so the test we use for that is known as the average nearest neighbor test. So here's what it does. So it's a test to determine if a point pattern or distribution is random, clustered, or dispersed. So the null hypothesis is that the point pattern is random. So there is no pattern. It's neither clustered nor dispersed. In contrast to that, the alternative hypothesis is the point pattern is not random, which means that the points must either be clustered or dispersed. A key component of this statistic is that you're not actually looking at the value stored on the points. You're just simply looking at the pattern of the points. So for example, if you had points that represented, say, discharge for like a mine outflows, you're not actually looking at whether near features have more similar outflows. You're just simply looking at the spatial distribution of the features. When we start looking at the actual values, that's different tests, which we'll look at later, and look at things like spatial autocorrelation. So again, it only looks at the spatial distribution of points, not the attributes stored on those points. And again, similar to some of our other earlier measures, this can be done using Euclidean distance, straight line distance, or the Manhattan distance summing the x and y directions. All right, so here's an example of some outputs from ArcGIS for assessing point patterns. So here we have a set of points, and the question is whether or not these points are clustered, random, or dispersed. The null hypothesis is that they're random. If they're not random, then they have to be either dispersed or clustered. These data were created using a random point generator, so they should roughly be random. However, if you look at the result of this test, we see that they show up to be dispersed. However, this is with a p-value of 0.06. So if we were using our 0.05 cutoff, this would be considered to be non-significant or random. I thought this was an interesting result because I did actually create this with a random generator, and I actually got a slight dispersed pattern. But again, that depends on your threshold. So note with this, we're basically comparing the observed mean distances between points, a point in its neighbors, or nearest neighbor, with an expected value. From that we get this nearest neighbor ratio, from that we get a z-score, and from that we can calculate a p-value. So just for comparison, this is a basically perfectly dispersed pattern. The points are evenly spaced out. So here we can see that we got a much higher nearest neighbor ratio, a very high z-score, and a very, very low p-value. So these data are very statistically significantly dispersed. They're not random, they're not clustered, they're heavily dispersed. In fact, they really couldn't be more dispersed by definition. And then looking at the other extreme, here we have some very clustered data, and now we can see that our results showed clustering. We got a low nearest neighbor ratio, a negative z-score, and a very low p-value. So again, this suggests that the data are clustered. Okay, kind of expanding upon this test, this is really just looking at global. So global pattern, is the data points randomly dispersed, clustered, or random, clustered, or dispersed. What if we were actually more interested in looking at how this pattern could change with scale? So looking at variable distances and seeing if you see different patterns with different distances. So that can be accomplished using the Ripley's K statistic. So it assesses patterns at multiple scales or distances as opposed to just a global statistic. So your result, you're actually going to get different measures of K values at different distances. They'll tell you whether the data at that distance is random, clustered, or dispersed. So when the observed K value is larger than the expected K value for a particular distance, the distribution is more clustered than a random distribution at that distance, which is, again, the scale of the analysis. And then when the observed value is actually smaller than the expected K value, the distribution is more dispersed than a random distribution at that distance. So you can kind of think about this as nearest neighbor, but instead of a global value, it's either globally clustered, random, or dispersed. You're trying to look at this more locally, so at different scales. Okay, so now we're going to move on to look at global spatial autocorrelation. So measures of spatial autocorrelation globally, so for the entire data set. Okay, so this the idea of spatial autocorrelation goes back to Tobler's first law of geography, which is basically that everything is related to everything else, but near things are more related than distant things. So according to this law, you would expect that features that are closer together tend to have more similar values than features that are further away. So, for example, if you had counties that are closer, you might expect them to have more similar, say, demographic data than just counties that are more spread apart. This was originally stated in this paper from 1970, so a computer movie simulating urban growth in the Detroit region, which was published in Economic Geography. So let's explore and discuss this concept of spatial autocorrelation. All right, so here is a simple explanation, hopefully, of spatial autocorrelation using kind of a checkerboard pattern. So here we have basically perfect clustering. So all the red values are clustered to one side, all the blues are clustered to the other side. So they're basically as clustered or grouped based on color that they possibly could be. On the other extreme, we have a dispersed pattern. So here there's an alternating red, blue. So this is basically as dispersed as you can make the colors in this checkerboard pattern. So completely clustered, completely dispersed. And then somewhere in the middle, we have basically a random pattern. So this would be randomly assigning certain cells to blue and randomly assigning certain cells to red. So note how this is different from the average nearest neighbor test we looked at earlier. Now we're actually interested in the attribute of the features as opposed to just their spatial pattern. So in this case, the attribute is simply red versus blue. All right, so there's different ways to look at and assess and quantify spatial autocorrelation. One of those is the semivariogram. So this is a semivariogram. So here's the definition. So it's a measure of the spatial dependence between two observations as a function of the distance between them. And it's basically equal to the squared difference of the two values. So, yeah. So, and then this semivariance is plotted on a semivariogram, where the x-axis is the distance between the points and the y-axis is the semivariance as defined here. All right, so here's a very simple cartoon conceptualized semivariogram with a couple things labeled. I'm going to go ahead and move on to the next slide because that explains some of these definitions, but it's got the same image. Okay, so the range is the distance where the model first flattens out. Okay, so that would be here. So the distance between points where the model flattens out, which basically means where the semivariance stops increasing. So basically things that are close in this are very similar, so they have a low semivariance, and eventually you get to a point where the semivariance or difference between the values really don't increase anymore, and that is the range. The semivariance value at which the range occurs is called the sill. Now, when at a distance of 0, you would expect to have basically a semivariance of 0, right? Because two features that are right on top of each other should basically have the same value because they're being measured at the exact same location. But that doesn't always happen. So this is explained here. So theoretically, at 0 separation distance, lag of 0, so at distance of 0, the semivariogram value is 0. However, at infinitesimally small separation distance, the semivariogram often exhibits a nugget effect, which is some value greater than 0. So you're actually seeing some difference at the same location. So what's the reason for that? So I'll just read this. So the nugget effect can be attributed to measurement errors, so errors in data precision and measurement at the same location, or spatial sources of variation at distances smaller than the sampling interval, or both. So imagine that you only sampled a data points every, say, 5 meters, but there actually were differences within that 5 meters. Or you're working with raster data and there's variability within the cell, even though the cell only gets assigned one value. Measurement error occurs because of the error inherent in measuring devices, so like meters and whatnot. Natural phenomena can vary spatially over a range of scales, so from small scale to very large scale. Variation at micro scale, smaller than the sampling distance, will appear as part of the nugget effect. So you're seeing noise that's smaller than, say, your measuring distance, spatially speaking. Before collecting data, it's important to gain some understanding of the scale of spatial variation, so how that impacts how you sample and what type of effect you would see. So again, this nugget effect is basically the semivariance at a distance of 0. So you can calculate what's called a partial CIL, which is a CIL with the nugget effect minused out. So kind of adjust for that non-zero semivariance at a distance of 0. So you might be thinking, well, this is, I guess, interesting graph, but what does this actually tell us about semivariance or autocorrelation? Well, what this is used for is to give you a sense of how the semivariance, which again is basically measures similarity or autocorrelation, varies with distance, which is the x-axis. So again, here we're seeing an increase in semivariance, or things become more different as they become further apart. But eventually, that just levels off, and you no longer have an increase in semivariance. One thing that's also confusing on a semivariogram is what the actual dots represent. In this case, each dot doesn't represent a single sample point, but instead it represents a pair of sample points. So each dot is is 2 sample points that are being compared. The x-axis is the distance between those 2 points, and the y-axis is the semivariance measure, so the difference between their values as described in the previous slide. So it's a bit confusing. So if you have a large sample and you have to do each pair, so say you have 100 samples, each sample will have to be paired with the other 99 samples, you can end up with a very large number of points. Before we move on, I wanted to say that this looks kind of simplistic, and it is generally much more complicated in reality. You're not generally going to get these nice orderly patterns where the semivariance levels off and it's very clear where the range is and the CIL and what the nugget effect is. Generally, real data are much more noisy than this. Okay, so that's kind of a graphical representation of autocorrelation. How do we actually measure autocorrelation statistically? Well, when we're interested in measuring autocorrelation statistically globally, so is the data globally spatially autocorrelated, we generally use the Moran's I statistic, which is arguably one of the most used statistics in GIS and spatial analysis and spatial science, spatial statistics. Okay, so what is Moran's I? So Moran's I is this. So measures spatial autocorrelation, so how similar or different near values are, values on near features are, based on feature location and attribute values using the global Moran's I statistic. The null hypothesis for this test is that the spatial pattern of attributes is random. So you don't really see any patterns in the values stored on the spatial objects. So near features don't have more similar values, or distant features don't have to have less similar values, or whatever. The alternative hypothesis is that there are spatial patterns of attributes, that the spatial patterns in the attributes is not random. So there's spatial clustering or dispersion. So again, spatial clustering would indicate that near features tend to have more similar values, whereas dispersion would actually indicate that near features actually tend to have more dissimilar values. Again, this can be calculated using a Euclidean distance or a Manhattan distance, and you have to conceptualize what you mean by spatial relationships or neighbors. Let's talk about that in a minute. Positive Moran's I values tend to indicate clustering, whereas negative Moran's I values tend to indicate spatial dispersion. Okay, so there's a lot of text on this slide. I just wanted to mention that there are different ways that we can conceptualize spatial relationships, and that will generally have an impact on the statistical test. So it's important to think about what of these options make the most sense for your situation. So just to go over a few of these, inverse distance is the following. So nearby neighboring features have a larger influence on the computations for a target feature than features that are farther away. So like inverse distance weighting. This is one of my favorite terms in GIS, zone of indifference. So features within the specified critical distance of a target feature receive a weight of 1 and influence computations for that feature. Once the critical distance is exceeded, weights diminish with distance. So near features have a really big impact, and then it trails off past the critical distance. This one I use a lot, contiguity edges only, so only neighboring polygon features that share a boundary or overlap will influence computations for the target polygon feature. So for example, if you were using counties, only the neighboring counties that actually share a value would be used as neighbors in the calculation. And there's a couple other options. So again, this is just introductory, but if you end up doing a lot of work with these type of analyses, you just kind of have to build up an understanding of when you should use these different methods, when are they applicable, and when are they potentially flawed to answer a certain question. All right, so here's some example output for a Moran's I, again, assessment of global spatial autocorrelation. Okay, so this is percent poverty data by census tract across West Virginia. So you can see the range there from up to 66% down to as low as like 11%. So the question here is there any spatial autocorrelation in this spatial distribution of poverty rates? So running the Moran's I test, we get a Moran's index of 0.25. We get a z-score of 8.9 and a very low p-value. So that indicated clustering. So at a very low p-value. So this would indicate that nearer features, in this case census tracts, tend to have more similar percent poverty rates than they would just by if they were randomly poverty rates were randomly assigned, right? So near features tend to have more similar poverty rates. That's the idea. So there's positive spatial autocorrelation or clustering. And just looking at this map, it's always good to visualize the data and think about whether or not it makes sense. In this case, I think it does make sense. Just looking at the distribution of the collars, it does seem to be some clustering of values. And also note this was done using contiguity edges only, so only neighboring census tracts were treated as neighbors in the calculation. Okay, another measure of global spatial global patterns is the GeoDIS or general G. So basically, Moran's I assesses the clustering of similar values. So does similar features tend to have more similar values? Are there clustering of high values and clustering of low values spatially? In contrast, this statistic specifically looks at clustering of high and low values across space. So specifically looking at high clusters and low clusters. So are high values clustered or are low values clustered? So the null hypothesis is that high values or low values aren't clustered. So it's random, there's no pattern. In contrast, the alternative hypothesis is that high and or low values are clustered. So there is a pattern, one or the other, low cluster or high clustered. Again, similar to the other tests, you can specify distance using Euclidean distance or Manhattan distance. You also must specify a conceptualization of spatial relationships similar to Moran's I. If you get a positive G value, that indicates a clustering of high values, as shown here. And if you get a low G, that indicates low clusters, so low values are clustered. Honestly, I tend to use Moran's I more often than I use this test, but I did want to mention it. Note that it is different. It's assessing high clustering and low clustering as opposed to just whether similar values are clustered or dispersed. Okay, so again, this was a significant high clusters example. Okay, so all those tests we just looked at were global measures. So in the end, you get a single statistic that it globally assesses, for example, spatial clustering using or spatial autocorrelation using Moran's I, or it looks at high and low clustering with the GeoDIS or general G. So now we're going to look at tests that look at more local patterns. Because as you could imagine, you could have areas in a map that are showing clustering, areas that are showing randomness, areas that are showing dispersion. So again, we're kind of scaling this to a more local scale as opposed to a global scale. And now we're generally going to get different measures across the map space as opposed to one global measure. Okay, so one option is the local indicators of spatial autocorrelation, or LISA statistic. So you can think about this as a local version of Moran's I. So it looks for the local patterns and the values associated with map features, as opposed again to a global pattern. The null hypothesis is that there is a local random pattern. The alternative hypothesis is that there is local spatial autocorrelation in the data, either dispersion or clustering, again relative to some attribute. Similar to the prior test, you can use Euclidean distance or Manhattan distance. You must specify again a conceptualization of spatial relationships, as discussed earlier. A positive I equals suggested features. Features have neighboring features with similar high or low attribute values. So basically clustering. And a negative I indicates that features have neighboring features with dissimilar values, so dispersion. There are a couple different groupings here. We can have HH, which is clusters of high values, LL, which is clusters of low values, HL, which is high values that are surrounded by low values, or LH, which is low values surrounded by high values. Here's an example output. So again, this is going back to that poverty data by census tract. So this is the census tracts with the college representing percent poverty. And here we have the results of our LISA analysis using a contiguity edges only spatial relationship. So here we have not significant patterns in like the white areas. We have our low lows. So these are areas low surrounded by low values of percent poverty, high, the reds here, high surrounded by high values, and this is the ones that are surrounded by, say, different values, the dark blues and dark reds. The test that I commonly use if I'm interested in exploring local spatial patterns is the hotspot analysis tool, which specifically looks at clustering of high and low values. And that's done using the GeoDIS or GI star statistic, as opposed to the general G, which is used for global patterns. So this is a local version, again, of the GeoDIS or general G. It looks at local clustering of high or low values. In this analysis, you end up getting hot spots or cold spots. So hot spots indicate clusters of high values, and cold spots indicate clusters of low values. Null hypothesis here is that no local clustering of high or low values exists. So again, it's a local test, and it's basically the null was random. Alternative hypothesis here is that the local clustering of high or low values do exist, and then those will be mapped. You can use Euclidean distance or Manhattan distance. Depending on how you want to define the distance relationships, you have to pick a conceptualization of spatial patterns. Again, a larger z-score indicates clustering of high values, small indicates clustering of low values. So here's an output from a hotspot analysis for population change between 2000 and 2010. So the blue areas indicate cold spots, and the red areas indicate hot spots, and the tan yellowish areas indicate no spatial pattern. So these counties would be counties that have experienced population decrease over that decade and are surrounded by counties that have also experienced a population decrease. And if you know anything about like demographic and population changes in the U.S., this actually makes a lot of sense. So we're seeing a lot of reduction in population in, say, Appalachia and also the area around Detroit. In contrast to that, the red areas are hotspots. So these would be counties that have experienced population growth and are surrounded by counties that also have shown population growth. And this should also make some sense if you know anything about trends in the U.S. So we're seeing a lot of growth, say, in the I-95 corridor between like Washington, Baltimore, Philadelphia up to New York. Some of the other very urbanized areas like Atlanta, the Denver area, Salt Lake City, the Northwest, and then like Southern California, Eastern Texas. So again, we're looking for clusters of high values, clusters of low values. This is the same text, just a different example. This is from Mike and Jackie Strager in the Davis College here at WVU. So this is showing block group, so census block group, and we're looking at the population of people over age 65. So again, the yellow areas would indicate no spatial pattern. Blue areas would be where there's clusters of low numbers of people over 65, so that would indicate a younger population. So for example, around Morgantown area, parts of the southern coal fields, out in the Panhandle. And then the red areas are clusters where there are a large number of older people over 65. So again, in this case, block groups have similar high values of people over 65. So Parkersburg area, Beckley area, Clarksburg area, Weirton, so on and so forth. So again, some interesting spatial patterns there around cities and some differentiation between cities, Morgantown versus Clarksburg, for example. And here's one more example of a hotspot analysis with the poverty data that we used earlier. So again, we're seeing clusters of counties that have high poverty levels here in the southern part of the state. So they have high population. They're surrounded by counties that also have a high population. And then, say, out here in the Panhandle, we're seeing clusters of counties that have a lower poverty rate. And again, surrounded by counties that also have a lower poverty rate. And then a lot of the middle of the state here, we're really not seeing significant hotspots or cold spots. I'm not showing it here, but just as a side note, it is possible to do these type of analysis over time. So look at changes in hotspots and cold spots and spatial patterns locally through time. So just a side note. Okay, so the last section of this lecture, we're going to talk very broadly about regression and how we can use the regression techniques in a geographic context and to, say, predict a variable using other variables. Okay, so what is regression used for? So first off, regression can be used to explore the relationship between variables, similar to how we looked at scatter plots and scatter plot matrices earlier. So are two variables positively correlated? One goes up, the other goes up. Are two variables negatively correlated? One goes up, the other goes down. Or is there really no relationship between them? You can predict a continuous variable using other variables. Regression is not used for classification. So, for example, using predicting types of land cover, for example. There are some alternative forms of regression allow for that, like logistic regression. But here we're talking about predicting something continuous, like chemical concentrations, like parts per million and parts per million, or percentages, or areas, or lengths, or whatnot. So a continuous numeric variable. Generally, we use this terminology. So the dependent variable is what you are trying to predict. It's the y variable. And the independent variable, or variables, if it's multiple regression, is what you're using to try to predict the independent variable. So for example, you could say that your weight is dependent on your height. So in that case, the dependent variable would be your weight, and the independent variable in this case would be your height. So the assumption is that your height impacts your weight as opposed to the other way around. Okay, so here's a layout for a single regression equation. So this is where you're trying to predict one thing with another thing. So there's one dependent variable, one y, and one independent variable, or one x. So this is a linear equation in your standard y equals mx plus b form, so slope-intercept form. So in this equation, y represents the true value being predicted, so the actual value of y. Y hat, so with this little symbol on top, that's the predicted value of y, so that's what the model or line predicts y to be. M is slope, so this is your, it's rise over run, so your slope of your regression line. The x is the predictor or independent variable, the thing you're using to predict y, so using your height, for example, is x to predict your weight y. B is the y-intercept, so this is the value of y when x is 0. So the value of your weight, for example, when your height is 0, which in that case really doesn't have physical meaning. And that's common where y-intercepts really don't have physical meaning. And this last component here is the residual or error term. So the part of y not explained by x. So to predict y, we basically take a slope, multiply it by our x value, and then add to that a y-intercept, and that gives us back our predicted value. If we add the e back to this, then we actually get the real value. So the model plus the error component gives back the actual measurement. So that's the form of regression equations. It's possible to expand regression to incorporate not just one, but many independent variables, so things that you could potentially use to predict y. So here's an example of a multiple regression equation. So we have beta 0, which is in this case the y-intercept. Then we have a slope, b1, associated with the first independent variable, x sub 1. Then we have another slope with the next independent variable, and the next variable another slope with another variable, so on and so forth. And at the end we have our error term, which is the portion of y the part of y not explained by the model. So the error plus the model yields the actual value. So for example, let's say you were trying to predict house value. So the y could be the values of the home. Then you'd have one predictor variable, so it could be like number of bathrooms. The second one could be number of bedrooms. The third one could be square footage. The next one could be like the school district that it's in, whatever. So you have a series of values that you're using to predict y. So basically in this context, what you're really doing is you're combining a bunch of variables with slopes and an intercept to try to estimate another continuous variable. That's the idea. One important component of regression analysis is the concept of residuals. So residuals are basically the difference between the actual value of y and the predicted value of y. In this graph, that's represented as the distance on the y-axis from the actual measurement, the blue dot in this case, and the predicted value of that measurement, which would be that location on the line. So that difference in y is the residual for that point. So to get the residual or error, you take the actual value of the sample, in this case the blue dot, minus from that the predicted value, where it falls along the line. And that difference is the error term or the residual. The portion, the amount of y not explained by the model. So again, it's the error. So generally when we're assessing the quality of a regression, we're generally looking at these residuals. So we want our residuals to be low, meaning that the actual values are very close to the predicted values, or the error term is of a small portion of it, or a small component of y. How do we actually assess regression models? So there's a couple different options. One that we've already talked about in the context of georeferencing is RMSE, or root mean square error. So again, this should be familiar to you. Basically, you take the error term, so the actual value of y minus the predicted value of y hat, so that's the error term. So you take all of those, you subtract, square, sum them up, divide by the number of samples, and then take the square root. So again, this is the same technique we use to assess georeferencing, except now we really only have one dimension for y as opposed to the x and y dimensions for our georeferencing. So when you take the square of this, so you're squaring it, and then you take the square root so that you're going to get the units back. So for root mean square error, the result will be in the units of the original analysis. So if you were trying, or of y. So if you're trying to predict, say, parts per million, your result's going to be in parts per million. You can also see a mean square error. I just noticed this is incorrect. This should be mean square error as opposed to root square error. So I was supposed to take out the root, but I took out the mean. So mean square error, MSE, is basically the same thing as RMSE, except you don't take the square root. So in that case, you're going to end up with the square of the units. So parts per million squared, percentage squared, length squared, whatever. So that's one way to do it. So with RMSE, we generally want lower values. The lower, the better. Another way to assess R squared, or assess regression, is using an R squared value. So R squared is basically the proportion of variance in Y explained by the model. This looks kind of complicated, but if you actually see what's going on here, it actually should make some sense. So the denominator here is the total sum of squares. What is that? Well, what it is, it's the value. Sorry, wrong one. Here we go. It's the value of y for each of the y's minus the average value of y squared and then summed. So that's really related to variance, right? So this is the total amount of variance in the model. So the difference between each sample and the mean value of the samples squared. So that's the total variance. And the top part of the equation is just that same total variance with the residual sum of squares subtracted out. So here the residual sum of square equation is the same as the total sum of square equation, except instead of using the average here, we're using the predicted value. So this is the error term. So the actual value minus the predicted value. So this is basically the variance that was not explained by the model. So if we take the total variance, subtract the unexplained variance, and then divide by the total variance, what we get back is the proportion of variance explained. So the total variance minus the residual is the variance explained, divided by the total variance, proportion of variance explained. Since this is a proportion, it's just simply scaled 0 to 1. So 0 would indicate that your model basically explained no variance in y, so it didn't really predict or explain anything about y. 1 would indicate that it predicted or explained all the variance in y, which frankly never really happens. So that's basically how that works. Again, 0 is bad, 1 is good. One thing nice about R squared is unitless. That it's unitless, so you can compare, say, models that are predicting different things. It's again unitless, so it's unit independent. As a side note with R squared, this is considered to be flawed when you do multiple regression or you have more than one X or more than one independent or predictor variable. So generally R squared will increase when you add predictor variables even if the model's really not increasing or improving. So we have to adjust for that. So this is the adjusted R squared. So you take 1 minus the R squared value times it by n minus 1, where n is the number of samples. So, the number of samples or training data, and then you divide by n minus p, which is the number of variables minus 1. So it's basically a correction for that inflation. The key thing you should know here is that adjusted R squared should be used when you do multiple regression. It's okay to use the original version of R squared if you do single regression. Okay, so here's a couple other points about R squared. I'm just going to read these real quick. So R squared is a statistical measure of how close the data are to the fitted regression line. It is also known as the coefficient of determination or the coefficient of multiple determination from multiple regression. Again, proportion of variance explained. The percentage of the response variable variation that is explained by a linear model. Again, that we explained that earlier. So explained variation divided by total variation. R squared is always between 0 and 100%, or if you're scaled as a percentage, or between 0 and 1 if it's a proportion. R-squared cannot determine whether the coefficient estimates and predictions are biased, which is why you must assess the residual plots, which we'll talk about briefly in a minute. So even though you get a high R-squared, there might be a problem with the model, which makes those results kind of flawed, or you can't really trust them. R-squared does not indicate whether a regression model is adequate. You can have a low R-squared value for a good model or a higher squared value for a model that does not fit the data, depending on your assumptions. Adjusted R-squared, again, one major difference between R-squared and the adjusted R-squared is that R-squared supposes that every independent variable in the model explains the variation in the dependent variable. It gives the percentage of explained variance as if all independent variables in the model affect the dependent variable, whereas the adjusted R-squared gives the percentage of variation explained by only those independent variables that in reality affect the dependent variable. So again, it's a correction. So the R-squared cannot verify whether the coefficient ballpark figure and its predictions are prejudiced. It also does not show if regression model is satisfactory. It can only show an R-squared figure for a good model or a high R-squared for a bad one. Okay, so again, one issue with regression is that it is what's called parametric. So it has assumptions. And if those assumptions are not valid, then that means that your results could be, you basically can't trust them. So what are the assumptions of regression? So the first is that there are linear relationships. So you're trying to model relationships using lines. So if there is no linear relationship, then that's obviously flawed. Another assumption is that the residuals are normally distributed. This can be assessed using the QQ plot. So the error or residual term should show roughly normal distribution. If they don't, then that indicates that your model is biased in some way. There shouldn't be a lot of multicollinearity, which means that the x's should not be, or the independent variables should not be heavily correlated with each other. And that's generally assessed using this variable inflation factor, or VIF statistic. You also shouldn't have autocorrelation in your data. So your independent variables, your samples should be independent of each other. Spatially, that can be assessed using the Moran's I statistic. And lastly, you should have homoscedasticity as opposed to heteroscedasticity. Basically what that means is that for homoscedasticity, which is what you want, you should see the residuals be roughly random for values of y. So you shouldn't have more or less error for different values of y. In contrast, for heteroscedasticity, you're going to see some type of pattern. So here, for example, we can see that there's more variability at high values of y. So this indicates that the model is doing a poor job when y is high and doing a better job when y is low. So this isn't preferred. You just want random noise. So the value of y doesn't impact the error or quality or residuals in the model. I didn't mention this plot. This is just showing a plot that allows you to compare linear relationships between a predictor variable and y. So as you can see here, most of these lines approximate this linear trend line. So these three variables seem to be linearly correlated with y, the dependent variable. However, this one you can see a bit of an arc, which suggests that that's not a linear relationship, so there may be an issue there. We're not going to get into this in lab. This is something we generally discuss in more advanced courses, but I wanted to at least go over some regression components here because it is a very big part of working with data, analyzing data, trying to understand relationships and make predictions. So it's important to understand that regression assumes some things about your data, and if those assumptions are not met, then that means that your results could be flawed. Okay, and then to finish this up, I wanted to mention another form of regression that comes up in spatial data analysis specifically. So both for regression and multiple regression and single regression, you're going to end up with a single equation at the end with your coefficients and whatnot, and your intercept for the entire space. But what if you had spatial autocorrelation, or that the relationship between your x variables and your dependent variable y actually vary across space? Well, in that case, it would be better if we could actually have local measures or local regression equations instead of a global regression equation. And that's what geographically weighted regression allows us to do. So again, what is the relation between y and x? What if the relation between y and x vary across space? In this case, a single regression equation could be misleading or weak. So it would be better if you could actually have different regression equations across the map space. So it is possible to create regression equations that change over space, and that's effectively what GWR, or geographically weighted regression, is. There will be a different intercept and coefficients across the map space. So here's an example of an output from a geographically weighted regression. So for each geographic unit, we actually get different intercepts and different coefficients for different of the x's or predictor variables. So it's not a single model, but a model that varies over space. So it's geographically weighted. Here we can see that in a raster-based representation of coefficients. So this is the y-intercept over a map space, and this is the coefficient for a certain x or predictor variable over a map space. And the key thing here is you can see that they vary. So there isn't one coefficient across the entire map space or one y-intercept across the entire map space. And this is because you actually get a more local regression equation, or you get a different equation for each geographic feature instead of one global model. So in short, this is a little above what we're going to do in here, but I wanted to mention this technique because it's very important in spatial analysis and GIS. You would use geographically weighted regression in situations where you would expect the relationship between the x variables, the independent variables, and your y variable, your dependent variable, to change over space. And this can also be useful when you have spatial autocorrelation in the data. So if you want to explore this or use this, this is something that's generally discussed in a more advanced spatial statistics or spatial analysis class, but I just wanted to mention it here. Okay, so that's the end of this lecture. It's a bit of a long one. I hope you found this interesting. It's a really fascinating field of study, spatial statistics in and of its own right. You'll do a lab on this, and I hope you find that these techniques are useful, and if you like it, think about taking an advanced course where you really dive into these techniques. All right, thanks.